Hey everybody, in this video I'll tell you how to draw and evaluate resonance structures using a tool called formal charge. And to walk through this, we're going to be drawing the molecule HCO3-. Technically, I guess this is an ion, but we'll call it a molecule because all those atoms are covalently bonded together. Anyway, let's get started. The very first thing you got to do is draw the Lewis structure. So I'm going to put that right here in this column that says incomplete Lewis structure, and you'll see why we're going to at first do the incomplete version. I'm going to go through these steps pretty fast, like arranging the atoms. First we'll start with CO3. The hydrogen atom in a particle like this is going to attach to the oxygens, just as like a general rule to know. And we'll just start filling out the rest of these electrons in the proper order, like first putting in single bonds, then putting in lone pairs, and I'm skipping all of the counting of the valence electrons that's going on in the background here just to save time. And if you distribute all of the electrons in this molecule, you get this right here. And we're going to leave this drawn like this, even though it is not totally done. This is incomplete, and we're doing that because leaving the molecule like this unfinished before we fix it by making double or triple bonds is a good way to understand what resonance structures are and how many there's going to be. So here's the deal. My central atom carbon does not have an octet. It only has 1, 2, 3, 4, 5, 6 electrons around it, which means this Lewis structure is technically unfinished. The central atom needs to have 8 valence electrons around it in almost all cases, and carbon is one of those cases. So right now this is not done. The way you fix that is by taking in lone pairs from the outer atoms, like these oxygens, and any of those 3 oxygens would work. And you're going to take those lone pairs and pull them in to different spots to make double bonds or triple bonds to give carbon the octet that it needs. This is where resonance structures reveal themselves, because with these 3 different bonds, there's 3 different ways you could do that. 3 different ways you can give carbon an octet, and I've actually drawn out one of them already right here. So let's start with that. If I took this lone pair on this oxygen in the top right hand corner and moved it in to make a double bond in that position, that would give carbon, let's draw that out really quick, that would give carbon the octet that it needs, and that also then is one of the possible resonance structures for HCO3-. But you should notice something about this molecule, and we're going to keep going back to our original incomplete structure. And what you should notice is that where we made the double bond in this top right hand position is not the only possibility. We could have also moved in a pair from this oxygen and made the double bond in that top left hand position. It solves this exact same problem in the exact same way, and drawing that version is drawing a second of the possible resonance structures. And by this point you should see that there is only one other reasonable option, and that is to use the lone pairs on this final oxygen, pull in one of those to make a double bond in this lower position like so. And since there's only 3 bonds around that carbon, there's really only 3 different spots we can put that double bond, and that's why HCO3- has these 3 possible resonance structures. So that would be step 1, is just draw out all your possibilities. Now we're going to get to the next part of this, which is evaluating those resonance structures with a thing called formal charge. Formal charge is a sort of like a test, a little numerical test it kind of just tells you whether the electron distribution you've got in your Lewis structure is a good one. And it's just a quick calculation where you take an atom's valence electrons that it should typically have, just like as an atom not bonded in a molecule, and from that you subtract out however many electrons are around it in the molecule currently, the way that you've got it set up, and that is the collected all the lone pair electrons it has, combined with half of any of the bonding electrons that it has. So that's a little formula that you can use to run these formal charge values. Let's do that in detail for just one atom so you can see exactly how it works, and then the rest I'll just sort of quickly fill out. But we'll start with this oxygen right here. Oxygen has 6 valence electrons. From that, I'm going to subtract however many lone pair electrons are around this atom. 1, 2, 3, 4 in this particular case, plus half of the bonding electrons. Now there's one bond here with 2 electrons and another bond here with another 2. So 4 total bonding electrons, but I'm going to take half of that for a total of 2. You can also think about that as just taking 1 electron from each of the bonds. This ends up being 6 minus 6, which of course is 0. And I just calculated that this oxygen has a formal charge of 0. If you apply that same formula to, let's try the carbon in the middle. Carbon has 4 valence electrons, minus no lone pairs and 1 electron from each bond. 1, 2, 3, 4. This carbon is also 0. This oxygen with the 2 bonds and the 2 lone pairs in the top right is going to be just like this oxygen, which also had 2 bonds and 2 lone pairs. So I know without even calculating that this one's going to be 0. This oxygen will calculate out. It's got 6 valence that it should have, minus 1, 2, 3, 4, 5, 6, 7 electrons around it right now for a total of -1. And this hydrogen here ends up being 0. I'm going to go ahead and do that for all of the atoms in each of these structures very quickly now. So I've gone ahead and done all the formal charges as well as kind of neatened up this first structure. So that part's done. The very last piece of this puzzle is, what do those formal charges mean? Are there some rules behind the value of these numbers? There's a couple guidelines that you need to know with formal charge. For this set of resonance structures, we only need the first one, and I'll just summarize this very simply. Zeros are what you want. If you're giving, if you're setting up the electrons in a Lewis structure, if an atom has a formal charge of 0, you have done a good job with that electron arrangement. So we can use that to kind of pick, of these resonance structures, are any of them better than the others? If you go down here to this resonance structure 3, there's only 2 atoms that actually have a 0. Oxygens have a -1. This oxygen has a +1. These other 2 guys, they'll have 4 different zeros and only 1 oxygen with a -1 charge. So even though I drew 3 resonance structures, you could sort of rule out this last one as being acceptable or a reasonable likely version of HCO3- that you might see in real life. That leaves us with these 2 resonance structures, and they are exactly equivalent to each other, at least in terms of formal charge, right? Each of them has 4 zeros. Each of them has a single -1, and the -1 is on an oxygen atom in both cases. So there's no way we can differentiate between those 2, which means they are both equivalent resonance structures for HCO3-. So that wraps it up for this video on drawing resonance structures and evaluating them with formal charge. Thanks a lot for watching.